morning. We're going to be talking about fuel systems a little bit this morning and how they work and things like that. We're going to talk about different kinds of fuel systems that we use on cars. So the first one we're going to look at is carburation, and this is a basic fuel system type that was used on cars from literally the late 1890s, or late 1800s, I should say, 1890s, up until the last computer-controlled carburetors that were being used were in the mid-1990s, so 100 years of them. A carburetor, like it says here, outside air pressure moving past a nozzle, and here's what we call a main discharge nozzle right here. Outside air pressure coming by that creates a low pressure. So, and it just says it draws fuel, but what it does, it creates a low pressure in what's called a venturi in here. Anyways, air coming down through draws fuel uphill against gravity, and it mixes with the air. So a carburetor is a fuel mixing device. And it, as you look, and this is a real basic, simple single barrel carburetor, that throttle plate would be controlled by your foot. This is called a choke plate. We won't worry about it for the moment. Here's a 4-barrel carburetor right here. Here's one I have in my hands right here. And this is a large Holley 4-barrel carburetor. Actually, it's a Motorcraft 4-barrel carburetor that's been kind of cut apart so you can see it. These are the 4 barrels here, these two. And a 4-barrel carburetor is, again, a fuel mixing device. So a single barrel, 2-barrel, 3-barrel, 4-barrel carburetors are all air fuel mixing devices. The amount of air and fuel, it says, that goes into the engine is dependent upon how far down you push this throttle valve open. So on a carbureted car, when you push the gas pedal, it actually lets air and fuel into the engine, whereas a fuel-injected car is quite a bit different. Again, a carburetor is a fuel mixing device. Okay, so it has what's called a venturi, which is a restriction in there that creates a low pressure to draw fuel uphill against gravity into the airstream. So this little narrowed area is what we call a venturi. So the air goes through and it speeds up, creates a low pressure, and draws fuel uphill against gravity into the airstream. So this air fuel mixing device that was used for roughly 100 years did a decent job in making power. It did a decent job in fuel economy. It did a not so good job in cold start, and did not so good job in pollution control. You can get decent fuel economy out of them, and you can get great power out of them. But again, emissions are poor, and cold start and drivability is not so good as well. It says atmospheric pressure and engine vacuum work to bring fuel into the engine. So it works on the difference of 2 pressures, outside air pressure, and then underneath the throttle plate there, what we call intake manifold vacuum, which is the descending motion of the piston creates a suction, and that's our vacuum. So at sea level, we have 14.7 pounds per square inch of air pressure. That's the weight of the column of the atmosphere above your head, if you will, when you're standing at sea level. That's outside air pressure. And inside the engine, we actually have a suction or a vacuum. So those 2 differences in air pressure is what draws in air and fuel into the engine, again, based on foot position on the throttle plate, etc. So that's a little bit about a carbureted system. But let's just step back for a moment and say, hey, what's the purpose of the fuel system? Well, we got to deliver gasoline and air into the engine, and we're going to compress them inside the cylinder at a very hot and explosive mixture. So if we compress gasoline and air together and we give it a spark, then we get an explosion which drives the piston down, if I suppose my fist is a piston, and so on. Okay, so our first fuel system type is a carburetor. Again, you won't see these on any cars before the mid-90s, and you won't see them on most any car, excuse me, and you won't see them on most any car since about I am stuck. Any American car since about the late 70s or early 80s. Okay, all right. So the next type of fuel system that was developed in the mid 80s is what's called a throttle body injection unit. And here's one here. This is a 2-barrel throttle body injection unit. And I have a 2-barrel Ford throttle body injection unit right here. It's got a fuel injector there, and it's got a fuel injector there. So there's 2 fuel injectors. And it says pressurized fuel is sprayed into the airstream through 1 or 2 centrally located fuel injectors. This one happens to be made by Holley for General Motors. That's, I believe, is the GM 2-barrel throttle body unit that's on my 92 Suburban. Okay. Now what we're doing is, instead of drawing fuel out of a nozzle uphill against gravity just by air pressure, now we're using an electric pump to create, anywhere on the low pressure side, some of these run about 15 psi, to a high pressure throttle body injection unit, which is about 30 psi. And we're actually spraying the fuel out in a nice cone spray. And one of the ways that I like to illustrate the difference between a carburetor and a throttle body injection unit is, I got a spray bottle here. And when I spray water out, it comes out very heavily droplets, if you can see it. And I don't know if the camera's picking it up. But when it comes out in fairly heavy droplets like that, that would be the same as what you see typically coming out of a carburetor. A fuel injector gives us this really nice coned, atomized air-fuel ratio mixture that's much easier to burn and to ignite. Consequently, throttle body injection units have better drivability, especially when cold starting. Gas mileage and power is about the same as a carburetor, but emissions are better. Okay, so drivability and emissions are better. The injector is going to atomize fuel because it's sprayed out under high pressure, like the spray bottle I just showed you, for improved burning in the cylinder, or I guess what we really should say, in order to, well, by atomizing it allows it to burn better. That's true, so improved burning in the cylinder. And then notice I have here computer sensors are used with a computer. Before 1996, we called it an ECM, electronic control module. Now, since 1996, we call it a PCM, or powertrain control module, to determine the time the injector is going to spray, or the pulse width. So we use a bunch of sensors to give input to a computer, and then the computer says, okay, spray the injector for this long, and then shut it off, and then spray it for this long, and then shut it off. So now we've got some other factors besides just our foot. Okay, we're looking at the temp of the engine, we're looking at outside air temperature, we're looking at pressure in the intake manifold, we're looking at vehicle speed and engine RPM and these kinds of things. All right. So the third and more common fuel system that's used today is what we call a multi-point or multi-port fuel injection system, what people call an MPFI or just PFI. And what it says here is that pressurized fuel is sprayed at the end of each intake manifold runner, just behind the intake valve. And let me show this to you. And first, here's a set of injectors. This is off a V6 engine. And so you've got 6 injectors that would spray at the back of the intake valve. And this is known as indirect fuel injection. So let me grab right here another intake manifold. This is a lower intake manifold from a Ford V6 from the new millennium. And what you're seeing here is this bolts down on top of a, actually this is a midsection of a lower intake manifold. And you can see the injectors here, these yellow orangish injectors are spraying, and the nozzle is right there. Okay, so there's a nozzle there. Here's a nozzle over here, right there. And that's spraying at the back of the intake valve. So that's one way that we do fuel injection. So what you've got here in this picture is actually showing direct injection, where the injector is spraying into the combustion chamber, not at the back of the intake valve. A number of modern cars today are both direct and indirect injection. So we have an injector in the combustion chamber, but we also have an injector spraying at the back of the intake valve. There's a number of reasons for that. We'd like to use just direct injection, but there's some problems that come with it. So a number of cars have gone, everybody used indirect injection from, let's say, the late 80s up until 2005-ish, depending on the car company. And then we started seeing direct injection, and then we started seeing problems with direct injection. And so 2015 to 2020, now 2021, we are seeing cars with both direct injectors and indirect injection, where it's pointing at the back of the intake valve. Let's continue on here just a little further. So in a fuel system that has multiport fuel injection, the atomization is further improved, meaning when we spray the fuel, we get a really nice atomized mixture of air and fuel. But one of the advantages, and my pictures here don't show it, the throttle body injection unit still had to spray down out of those two barrels, and going by those barrels and then going down and turning corners as it goes down into the cylinders, air and fuel would tend to separate, and so your mixture wouldn't be as well atomized, and so it wouldn't burn as well. With port fuel systems, and that injector spraying at the back of the intake valve, or even better yet, spraying into the combustion chamber, you've got a better atomization going on, and so consequently it burns a little better. So we're going to use some sensors and a computer, PCM, to accurately determine the injector on time that we call pulse width. Okay, that's our pulse width, the on time of it. And what you're seeing in this picture here, that's a throttle position sensor, and this is a coolant temperature sensor, and this is what's known as a mass airflow sensor. This one tells the computer how far open you have the throttle plate and the rate at which you opened it. This one tells how hot the coolant system is. This one tells how much air is coming in. And the reason why we use these and other sensors is they're going to help the computer decide how long it should spray the injector at any given moment, depending on what the vehicle's encountering: a hill, going uphill, going downhill, flat ground, stop and go traffic, your foot on the pedal, foot off the pedal, etc. Sensors go like this: a TPS, or throttle position sensor. Okay, again, to tell the rate of opening and how far open you are. A MAP or MAF sensor, and this one happens to be a MAF, or a mass airflow. Manifold absolute pressure is kind of an earlier device to measure the amount of incoming air. And then this one's an ECT, or coolant temp sensor. So those are the three that I just mentioned there. Throttle position sensor, okay, mass airflow sensor, and then coolant temperature sensor to measure the temperature of the cooling system. Again, based on these and other sensors, the computer is going to decide how much fuel to spray. We're also going to look at how fast the engine's spinning. We're going to look at it through the crankshaft position sensor to give us the revolutions per minute that the engine's spinning, how fast it's spinning. Okay, and cars have vehicle speed sensors as well. So you know that engine speed can vary based on gear ratios, etc. So we also need to look at vehicle speed to decide where we are. Okay, let's pause here for a bit. So next we're going to just look at one other slide here on other fuel system components that are involved in delivering fuel and air to the engine and burning them in the right ratio so that they burn properly, giving us good power, good gas mileage, and hopefully minimal pollution. So all fuel systems include these parts. So we have a fuel pump. This is an electric fuel pump. And oftentimes they're in the bottom of the fuel tank, like this from a Chevrolet S10. This was an electric fuel pump, right, sitting right there, and it sits down on the bottom of the tank, and this is the float to tell you how much fuel you have on your gauge. That small, a little electric fuel pump will usually run on indirect injection systems about 30 psi, roughly 30 to 42 psi, and if you have a direct injected system that is a camshaft driven mechanical pump, they'll usually have one of these in the tank to push fuel up to that mechanical pump, and then that pump will make many times 1700 to 2000 psi. on direct injection. So really different on direct injection. We have a fuel filter, and this is a fuel filter here, and it's a pleated paper filter on the inside. So I've got one cut apart here. So here's a fuel filter that I've cut apart, and there's a little pleated paper filter. And as the fuel goes through the paper element, and any particles get stuck inside on that paper. And we've, since the early new millennium, in California in particular, I think, it's probably federally, that we have stopped putting filters outside of the gas tank. So all of our filters are in the gas tank now. And so they're not easily serviceable usually. But I have always recommended replacing fuel filters every year at 15,000 miles. The industry's usually accepted interval is every 30,000 miles. We have fuel lines, which are just metal lines like I have here, that are just running the fuel around to the injectors from the pump, etc., and running the length of the car. They're usually stainless steel, or they're a plastic. Okay. Then we have fuel injectors, and so here's a couple of injectors. They're little electrically operated solenoids that just have a coil and a plunger, and it lifts up to let fuel spray out. And the really cool principle that the solenoid works on is electromagnetism. If you take a coil, if my hand is a coiled wire, and this is a metal rod, and I offset it with a spring, and then I energize this coil, it'll pull the plunger in and center it in that magnetic field. And so we're able to have this on-off kind of movement for all different types of mechanical applications. Okay, I think this is one more there. So lastly, or number 5, is the intake manifold. This is our intake manifold. It's a series of runners to deliver the air and fuel. So air comes in this manifold here. The throttle body would sit here, and that's where the throttle plate is. So a throttle body would look something like this, where you push the throttle with your foot. This one is cable driven, and now all of our cars are drive-by-wire, so they're electric. They have a little DC motor that turns the throttle plate now. And that throttle body is going to let the air into the intake manifold. The length, what's going on is we're not only distributing air and fuel to the right cylinder at the right time, but we're putting the air through a tube with a certain amount of length. And a longer, smaller tube tends to build torque, and a shorter, larger tube tends to build horsepower. So we can do things to help the power of the engine based on intake manifold design. Just an FYI, something mechanical engineers look at really carefully. I think that's it. So that's a little bit on fuel systems in cars. Okay. Just as a comment, fuel systems today on modern vehicles are very bulletproof. There's very few things that go wrong. There's very little servicing needed. We can run a fuel system cleaner every other year at 30,000 miles perhaps through the fuel system to keep the injectors tips kind of cleaned out. Changing the fuel filter, if it's easily done, we can do that. But other than that, fuel systems are very, very bulletproof, and about the only thing that fails is the fuel cap seal, and we tend to get a fuel evaporative emissions code that is indicated by the check engine light being on. But otherwise, there's not very much maintenance, and there's not very many problems that are associated with fuel systems anymore like there used to be with carburetors and things like that. All right, that's it for now. Thank you so much.